Picture yourself standing beneath a dark sky, far from any city lights, gazing upward at the pale river of stars stretching across the heavens. That soft glow is our galaxy, the Milky Way, yet most of what you see is merely the surface, the visible face of something far vaster and stranger. Behind that familiar light lies a realm of cosmic dust, invisible matter, hidden black holes, and ancient secrets that never reach our eyes. This is a sleep documentary about the unseen, and these sleepy science facts will help you fall asleep fast as we explore the hidden depths of our galactic home. Tonight in this documentary for sleep, we wander through the shadows of our galaxy, where light cannot travel and telescopes struggle to see. From vast clouds of dust that block the view of distant stars to the mysterious dark matter that holds everything together without ever revealing itself, the Milky Way hides more than it shows. These are gentle facts for deep sleep, where the unknown becomes a lullaby. Welcome to Drowsy Discovery. Over the next 2 hours, over 100 gentle facts will drift through the darkness like starlight struggling through cosmic dust. There is nothing to memorize, nothing to remember. Just listen and let your mind wander into the unseen corners of the universe. Have you ever wondered what lies beyond the stars you can see, in the spaces where light does not reach? You are not alone. If these science facts bring you comfort, consider subscribing to join our community of curious sleepers, one peaceful night at a time. Now let your breathing slow, let the tension in your body begin to fade, and feel yourself settling into the quiet. The dark is not something to fear tonight. It is simply the canvas upon which the universe paints its most patient secrets. Let us begin. The Milky Way contains more hidden matter than visible stars. When you gaze at the night sky, the glittering stars you see represent only a small fraction of what our galaxy truly contains, for the Milky Way is a place where the invisible far outweighs the visible. Astronomers estimate that for every star shining in the heavens, there exists roughly 6 times as much matter that emits no light at all, hidden in vast clouds of gas, in cold dust drifting between the stars, and in the strange substance known as dark matter. If you could somehow weigh our entire galaxy, you would find that the brilliant stars, the burning suns that seem so dominant, account for less than 15% of the total mass, while the rest remains cloaked in shadow, exerting its gravitational influence without ever revealing itself. The universe we see is merely the surface of something far deeper, like a candle flame flickering above an ocean of darkness. Cosmic dust clouds block our view of most of the galaxy. Scattered throughout the Milky Way are immense clouds of cosmic dust, tiny particles of carbon, silicates, and ice that drift like fog between the stars, and these clouds are so vast that they obscure our view of most of our own galaxy. When you look toward the center of the Milky Way on a dark summer night, you are not seeing empty gaps in the starfield. You are seeing the shadows cast by dust clouds lying between us and billions of stars beyond. These particles are unimaginably small, yet collectively they form curtains of darkness stretching thousands of light years, blocking the light of distant suns. If our eyes could see through this cosmic veil, the night sky would blaze with brilliance we cannot imagine, but instead we peer through scattered windows, glimpsing fragments of the stellar tapestry that surrounds us. The dust both conceals and creates, for from these dark clouds new stars are born. The galactic center is invisible to ordinary light because of intervening dust. At the very heart of our galaxy, some 26,000 light-years away, lies a region of extraordinary activity where millions of stars crowd together around a supermassive black hole, yet we cannot see it with ordinary light. Between us and the galactic center stretch countless clouds of dust, absorbing visible light so completely that not a single photon from that distant core reaches our eyes. For centuries, astronomers wondered what lay at the center of the Milky Way, glimpsing only the bright band of stars that marks the galactic plane, while the true heart remained hidden. It was only when we learned to observe in infrared and radio wavelengths that we finally saw through the veil and discovered the crowded stellar metropolis at the center. The galactic core blazes with activity, yet hides in plain sight, separated from us by veils of shadow. We live in a galaxy whose center we can never truly see. Sagittarius A-star is a supermassive black hole at the heart of our galaxy. At the precise center of the Milky Way, in the direction of the constellation Sagittarius, there lurks an object of almost unimaginable power, a supermassive black hole that astronomers have named Sagittarius A-star. This gravitational giant sits at the pivot point of our galaxy, the anchor around which hundreds of billions of stars slowly orbit, yet it emits no light of its own and can only be detected through its effects on nearby matter. For decades, astronomers watched stars near the galactic center moving in strange rapid orbits, their paths revealing something enormously massive yet invisible. And gradually, the evidence became overwhelming that a black hole occupied that central point. Today, we have captured an image of the shadow cast by this black hole against glowing gas, a dark silhouette in a ring of fire. Sagittarius A-star waits in darkness at the heart of our galaxy, patient and eternal. This central black hole has the mass of 4 million suns compressed into a single point. The supermassive black hole at the center of our galaxy contains within its event horizon the equivalent of 4 million suns, all that matter compressed into a region smaller than the orbit of Mercury around our sun. If you could gather 4 million stars and squeeze them together, the gravitational pressure would crush them into a singularity, a point of infinite density where normal physics ceases to apply. The event horizon of Sagittarius A-star, the boundary beyond which nothing escapes, stretches roughly 24 million kilometers, large enough to swallow our solar system to the orbit of Mars. Yet despite its enormous mass, this black hole is remarkably quiet, consuming very little material and emitting only faint flickers of radiation as wisps of gas spiral inward. It is a sleeping giant, holding the galaxy together while remaining hidden. Such power compressed into such silence. And from the dense heart of the galaxy, we drift outward into the vast dark halo that surrounds us like an invisible ocean. The Milky Way is surrounded by an enormous halo of dark matter, enveloping our entire galaxy, stretching far beyond the outermost stars. There exists a vast spherical cloud of matter that we cannot see or detect with any telescope, yet its presence shapes everything we observe. This dark matter halo extends perhaps 1 million light years from the galactic center, dwarfing the visible disk that measures only 100,000 light years across, wrapping around the Milky Way like an invisible ocean. We know this halo exists because stars at the edges of the galaxy orbit faster than they should if only visible matter were pulling on them, revealing something massive yet hidden. The dark matter halo contains no stars, emits no radiation, and interacts only through gravity, yet it is the scaffold upon which our galaxy was built. You exist within this invisible embrace right now, surrounded by matter that has never been seen. It is everywhere, yet it remains mysterious. Dark matter makes up roughly 85% of the galaxy's total mass. When astronomers calculate the total mass of the Milky Way, accounting for every star, planet, and cloud of gas, they find that visible matter represents only about 15% of what the galaxy weighs, while the remaining 85% consists of dark matter never directly observed. For every kilogram of ordinary matter, there exist roughly 6 kilograms of this mysterious substance, silently exerting gravitational pull on everything around it. The stars you see, the planets orbiting them, even your own body, are made of matter that is cosmically rare, outnumbered by something we cannot detect except through gravity. Dark matter does not emit light, does not absorb it, does not interact with radiation in any way we can measure, yet it dominates the mass of our galaxy and the entire universe. We live as small, bright sparks within an ocean of darkness. What exactly is dark matter remains unknown. We cannot see dark matter, but we can detect its gravitational pull on visible stars. Although dark matter remains invisible to every telescope we have built, we know it exists because we can see its effects on things we observe, like watching wind move through trees though the air is invisible. Stars at the outer edges of galaxies orbit at speeds that would fling them into intergalactic space if only visible matter held them, yet they remain bound by gravity of something unseen. When astronomers noticed this in the 1970s, they realized either our understanding of gravity was wrong, or there was far more matter than telescopes could reveal, and decades of research confirmed dark matter is real. We see it bending light from distant galaxies, warping spacetime like an invisible lens. We see it shaping the universe, drawing galaxies into clusters. We feel its presence everywhere, though it never shows itself. Dark matter whispers through gravity alone. Without dark matter, the Milky Way would fly apart as it rotates. The Milky Way rotates slowly around its center, taking our solar system roughly 230 million years to complete a single orbit, and at these speeds, visible matter alone would be insufficient to hold the galaxy together. Stars at the outer edges orbit at velocities that would send them flying into intergalactic space if only visible stars and gas were pulling on them, yet they remain bound, circling faithfully around the galactic center. Dark matter provides the gravitational glue that holds everything in place, its immense mass creating a deeper gravitational well than visible matter could produce alone. If dark matter vanished, the outer regions would unravel, stars drifting into the void, the spiral structure dissolving into chaos. The very shape of the Milky Way, the spiral arms, the disk, all of it depends on invisible scaffolding. We owe our existence to something we have never seen. The dark matter halo extends far beyond the visible disk of the galaxy. While the glittering disk of the Milky Way stretches roughly 100,000 light-years across, the dark matter halo extends far further, reaching perhaps 1,000,000 light-years into intergalactic space. If you could visualize both together, you would see a small bright disk at the center of an enormous spherical cloud of invisible matter, like a coin resting inside a beach ball. This halo is not evenly distributed, but contains clumps and streams of dark matter, subtle variations reflecting the galaxy's history and the smaller galaxies absorbed over billions of years. The outermost reaches blend into the cosmic web connecting all galaxies, dark matter filaments threading through the universe like an invisible nervous system. Our visible galaxy is merely the glowing center of something far larger. We are a small island of light in an ocean of darkness. Billions of rogue planets drift through the galaxy without any star to orbit. Wandering through the darkness between stars are countless worlds that belong to no sun, planets either born alone or flung from their home systems long ago, now drifting endlessly through the void. Astronomers estimate there may be billions of these rogue planets in the Milky Way, perhaps even more than stars, each one a frozen wanderer traveling without warmth or light to guide it through eternity. Some may retain internal heat from their formation, maintaining liquid oceans beneath icy shells, while others have cooled to near absolute zero, becoming invisible against the black backdrop of space. Surveys using gravitational microlensing have revealed these wanderers passing in front of distant stars, their gravity briefly bending starlight and betraying their presence. They drift in silence, countless orphaned worlds that we will never see. And from these wandering worlds, we turn to the hidden stars that shine too faintly for our eyes to ever see. Most stars in the Milky Way are dim red dwarfs invisible to the naked eye. Although we think of stars as brilliant points of light, the most common stars in our galaxy are so dim that not a single one can be seen without a telescope, despite there being tens of billions of them scattered throughout the Milky Way. Red dwarfs are small, cool stars that burn their hydrogen fuel so slowly they can shine for trillions of years, far longer than our universe has existed, yet they produce so little light that even the closest ones remain invisible to unaided human eyes. Proxima Centauri, the nearest star to our Sun at just over 4 light-years away, is a red dwarf, yet it is too faint to see without optical aid. These dim stars make up roughly 70% of all stars in the galaxy, a vast hidden population burning quietly in the darkness. If you could see them all, the night sky would be filled with a soft red glow, but instead they remain forever hidden from our sight. Brown dwarfs are failed stars that never ignited nuclear fusion. Scattered throughout the galaxy are objects that almost became stars but fell just short, gathering enough mass to collapse from gas clouds, yet not quite enough to ignite the nuclear furnace that powers true stars. Brown dwarfs occupy a strange middle ground between planets and stars, larger than Jupiter but smaller than the smallest red dwarfs, glowing faintly with heat from their formation, but never achieving the sustained fusion that would make them shine like the sun. They glow dimly in infrared wavelengths invisible to our eyes, slowly cooling over billions of years until they become virtually undetectable against the dark backdrop of space. Astronomers estimate there may be as many brown dwarfs as stars in the Milky Way, perhaps tens of billions of these failed suns drifting through the cosmic darkness. They are the almost stars, forever suspended between two states of being. Thousands of stellar remnants float through the galaxy as white dwarfs cooling in silence. When stars like our Sun exhaust their nuclear fuel, they shed their outer layers and leave behind a dense core called a white dwarf, a glowing ember roughly the size of Earth but containing half the mass of the Sun. These stellar remnants are born extremely hot, glowing white with residual heat, but over billions of years, they slowly radiate this warmth into space, growing ever dimmer as they fade toward darkness. The Milky Way contains billions of white dwarfs, the accumulated remains of stars that died throughout galactic history, continuing to cool for trillions of years until they become cold, dark objects no longer visible. Countless white dwarfs drift through our galaxy at various stages of this eternal cooling, some still glowing brilliantly, others fading to a dull red. They are quiet ghosts, slowly surrendering their light. Neutron stars are collapsed cores spinning hundreds of times per second in the dark. When massive stars explode as supernovae, their cores can collapse so violently that protons and electrons are crushed together to form neutrons, creating an object so dense that a teaspoon of its material would weigh billions of tons on Earth. These neutron stars are typically only about 20 kilometers across, smaller than a city, yet they contain more mass than our Sun, spinning at incredible speeds as they preserve the angular momentum from the larger star that created them. Some rotate hundreds of times every second, their surfaces moving at a significant fraction of the speed of light, emitting radiation beams that sweep through space like cosmic lighthouses. We detect these as pulsars when their beams point toward Earth, but countless others spin in darkness, their beams never reaching us. They are nature's most extreme objects. And as these hidden lights drift through your mind, let your breath become slow and steady. There is no need to hold onto any of these facts. Let them pass through you like distant starlight and feel your body sink a little deeper into rest. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's. Among the most extreme objects in the universe are magnetars, a rare type of neutron star possessing magnetic fields so powerful they would tear apart any matter that approached, stripping electrons from atoms at a distance of thousands of kilometers. These fields are roughly 1,000 trillion times stronger than Earth's magnetic field, so intense they would erase the data on every credit card on the planet from halfway across the solar system. Magnetars occasionally release enormous bursts of energy called starquakes when their crusts crack under magnetic stress, sending waves of radiation detectable across the galaxy. Only about 30 magnetars are known in the Milky Way, but millions more may have faded below our ability to detect them, silent yet possessing fields that would devastate anything nearby. They are cosmic extremes, reminders of forces far beyond anything we can create. Stellar mass black holes hide throughout the galaxy, remnants of massive stars that collapsed. When the most massive stars reach the end of their lives, their cores collapse so completely that not even light can escape, forming stellar mass black holes that drift invisibly through the galaxy. These black holes typically contain between 5 and 50 times the mass of our Sun, compressed into a region so small that their event horizons may measure only tens of kilometers across. Unlike the supermassive black hole at the galactic center, stellar mass black holes are scattered throughout the Milky Way, the remnants of massive stars that exploded long ago, now wandering invisible and undetectable unless they pass near something we can observe. Most consume nothing, emit nothing, and reveal themselves only through subtle gravitational effects on nearby stars. They are the invisible graves of giant stars, silent monuments to stellar death. The Milky Way may contain over 100 million stellar black holes. Based on the number of massive stars that have lived and died throughout our galaxy's history, astronomers estimate the Milky Way may harbor over 100 million stellar mass black holes, a population so vast it is almost beyond comprehension. If you could somehow see these invisible objects, you would find them scattered throughout the galactic disk and halo, the accumulated remnants of countless supernovae over the past 13 billion years. Yet despite their enormous numbers, we have directly detected only a few dozen, those that happen to have companion stars or are actively consuming gas and emitting X-rays. The remaining 100 million drift in silence, neither emitting nor reflecting any light, invisible sentinels scattered throughout a galaxy filled with hidden gravitational traps. Most of them will never be detected by any telescope we build. Most of these black holes are invisible because they are not actively consuming matter. Black holes are often imagined as cosmic vacuum cleaners constantly devouring everything nearby, but in reality, most stellar black holes drift alone through the vast emptiness between stars, far from any gas or dust they might consume. A black hole only becomes visible when material falls into it, heating to extreme temperatures and emitting X-rays before crossing the event horizon. But in the enormous spaces of the galaxy, most black holes encounter nothing to eat for millions of years at a time. Without infalling matter, they emit nothing, reflect nothing, and remain completely invisible against the dark backdrop of space, betrayed only if they pass in front of a distant star and bend its light through gravitational lensing. Right now, a black hole could be drifting through our solar system, and we would never know. They are perfect voids. We have only detected a tiny fraction of the black holes that exist in our galaxy. Of the estimated 100 million stellar black holes scattered throughout the Milky Way, we have confirmed the existence of only a few dozen, a detection rate so low it borders on absurd. The black holes we know are the exceptional ones, those in binary systems with visible companions, or actively consuming gas and emitting X-rays, while the vast majority remain forever hidden in the cosmic darkness. Gravitational wave observatories have begun to reveal black holes merging in distant galaxies, and microlensing surveys occasionally catch a wanderer bending background starlight, but these glimpses represent only the tiniest sample of what truly exists. For every black hole we detect, there are millions more drifting unseen, each one a permanent scar in space-time. We are only beginning to understand how many invisible graves the cosmos contains. And from the silent black holes scattered like invisible anchors, we move to the cold molecular clouds where new stars wait to be born. Giant molecular clouds are stellar nurseries hidden in the darkest regions of the galaxy. Scattered throughout the Milky Way are enormous clouds of cold gas and dust so dense that light cannot penetrate them, and within these dark regions, new stars are slowly being born. Giant molecular clouds are the great nurseries of the cosmos, containing vast reservoirs of hydrogen and helium gas, all waiting to collapse under gravity and ignite into new suns. These clouds appear as dark patches against the starry background, blocking the light of distant stars and creating shadowy lanes visible in the Milky Way. Inside them, gravity works silently, pulling gas together into denser knots until pressure and temperature rise high enough to trigger nuclear fusion and a new star blazes into existence. Most stellar births occur hidden from view, veiled by the dust that provides the raw material for creation. Stars are born in darkness. These clouds can stretch across hundreds of light years, containing enough gas to form millions of stars. The largest molecular clouds in our galaxy are truly enormous structures, spanning hundreds of light years across and containing enough gas to form millions of stars if conditions are right. A single giant molecular cloud may contain several million times the mass of our Sun, enough material to populate an entire region of the galaxy with new stellar systems. The Orion Molecular Cloud Complex, one of the closest star-forming regions, stretches across hundreds of light years and is actively producing stars even now. Within these vast structures, smaller, denser regions called cores begin to collapse independently, each potentially giving birth to a star or a cluster of stars. The scale is almost impossible to comprehend, structures so large that light takes centuries to cross them. They are the factories of the cosmos. Inside, the clouds' temperatures drop to just a few degrees above absolute zero. Within the dense cores of molecular clouds, temperatures plummet to extraordinarily low levels, often reaching just 10 or 20 degrees above absolute zero, making them among the coldest places in the universe. At these frigid temperatures, gas molecules move sluggishly, and the thermal energy that might resist gravitational collapse is largely absent, allowing gravity to slowly gather material. Astronomers measure these temperatures by observing faint radio emissions from molecules within the clouds, each type producing characteristic signals that reveal conditions inside. The cold is so extreme that exotic molecules form that could never exist in warmer environments, and ices coat the tiny dust grains drifting through darkness. In these frozen depths, the slow, patient work of star formation proceeds over millions of years. Creation begins in the coldest silence. New stars are forming right now in regions we cannot see with visible light. At this very moment, as you listen in the quiet of the night, new stars are being born all throughout our galaxy in regions completely hidden from our view. The dense dust surrounding forming stars absorbs visible light so effectively that optical telescopes cannot penetrate these stellar nurseries, leaving the births of new suns hidden from our eyes. Deep within molecular clouds scattered across the Milky Way, gas is collapsing, spinning into disks, heating up as gravitational energy converts to thermal energy, and eventually igniting nuclear fusion to begin new stellar lives. Thousands of these births occur simultaneously across the galaxy, each invisible to ordinary observation, each a miracle of physics in the cosmic darkness. We cannot watch these stars emerge, yet we know they are there. The universe creates constantly, mostly in secret. Infrared telescopes reveal the hidden glow of stars being born within the dust. Although visible light cannot escape the dusty cocoons surrounding newborn stars, infrared radiation can penetrate this veil, allowing specially designed telescopes to peer into stellar nurseries and witness creation. Infrared light has longer wavelengths that can pass through tiny dust particles, blocking shorter wavelengths, much like radio waves passing through walls that stop visible light. Space telescopes like Spitzer and the James Webb have revealed stunning images of star-forming regions, showing embryonic stars surrounded by disks of material that may form planets. In infrared vision, dark molecular clouds glow with warm light of protostars, objects not yet hot enough to shine visibly, but already radiating in infrared as they collapse. These observations have transformed our understanding of how stars form. We have learned to see through the veil. The Orion Nebula visible in our sky is just one small window into these stellar nurseries. On clear winter nights, you can see a fuzzy patch of light in the sword of Orion that marks one of the few places where we can glimpse star formation with the naked eye. The Orion Nebula is a cavity carved from a much larger molecular cloud by the fierce radiation of young massive stars, and through this opening, we peer into an active stellar nursery roughly 1,300 light-years away. Within this glowing region, astronomers have identified hundreds of young stars, many still surrounded by protoplanetary disks from which planetary systems may form. The Orion Nebula represents just a tiny fraction of star formation occurring throughout our galaxy, a single window into a vast process normally hidden from view. Most stellar nurseries lack such windows, their newborn stars completely hidden. We are fortunate to have this glimpse. And from the birthplaces of stars, we venture into the cosmic dust itself, the dark curtain that shapes what we can and cannot see. Cosmic dust is made of tiny particles of carbon silicates and ice. The dark dust scattered throughout our galaxy is composed of incredibly small particles, mostly carbon compounds and silicate minerals coated with layers of frozen water, carbon monoxide, and other ices. Each grain is typically smaller than a micrometer, far tinier than a human hair, yet these particles collectively have profound effects on everything we observe. Cosmic dust forms in the outer atmospheres of dying stars, ejected into space where it drifts through the interstellar medium for millions of years before being incorporated into new stars and planets. Some dust carries complex organic molecules, the building blocks of life, created in cold darkness between stars. When light passes through dusty regions, short blue wavelengths scatter while longer red wavelengths pass through, giving distant stars a reddish tint. Dust both obscures and reveals. A single grain of cosmic dust is smaller than a human hair, yet collectively they block entire regions of the galaxy. It seems almost impossible that particles so small they cannot be seen with the human eye could block our view of billions of stars. Yet this is precisely what cosmic dust does throughout the Milky Way. Each grain is typically less than a micrometer across, roughly 100 times smaller than a human hair, but there are so many particles spread across such vast distances that their combined effect is profound. When we look toward the galactic center, we peer through thousands of light years of dust-laden space, and cumulative absorption dims distant starlight by factors of millions. The dust forms a thin haze distributed throughout interstellar space, and over great distances, this haze becomes effectively opaque. Some regions are so obscured that not a single photon of visible light reaches us. Smallness multiplied becomes darkness. The Great Rift in the Milky Way is a dark lane caused by dust clouds blocking distant stars. When you look at the Milky Way on a clear, dark night, you may notice that the band of light is not uniform, but divided by a dark lane running along much of its length, a feature astronomers call the Great Rift. This dark division is not an absence of stars, but rather a series of dust clouds lying between us and the more distant stars of the galactic disk, blocking their light and creating the illusion of emptiness. The Great Rift stretches from the constellation Cygnus through Sagittarius, spanning much of the summer sky in the northern hemisphere, and it represents one of the most visually striking effects of interstellar dust. Behind this dark curtain lie billions of stars that we simply cannot see, their light absorbed by the countless dust grains floating in the intervening space. The rift reminds us that our view of the galaxy is limited and partial. We see only what the dust permits. Ancient cultures saw this dark band and wove it into their myths as a river or a road. Long before astronomers understood that the dark lanes in the Milky Way were caused by dust, ancient peoples around the world looked up at these same features and created stories to explain what they saw. The Aboriginal Australians saw the dark spaces as a great emu spread across the sky, its body formed by the darkness rather than the stars, while the Inca of South America recognized dark cloud constellations representing animals they knew from their lives. Many cultures interpreted the bright band of the Milky Way as a celestial river, a road for souls, or the backbone of the night, with the dark rift seen as pools, crossings, or sacred passages. These stories remind us that humans have always sought meaning in the patterns of the cosmos, even in the absences and shadows. The darkness that now reveals hidden physics once inspired mythology. Our ancestors gazed at the same mysteries we study today. Without cosmic dust, stars and planets, including Earth, could never have formed. The tiny particles of dust drifting through the galaxy may seem insignificant, but without them, the formation of stars and planets would be virtually impossible. Dust grains provide surfaces where hydrogen molecules can form, enabling the gas to cool efficiently enough to collapse under gravity and create new stars. In the disks surrounding young stars, dust particles collide and stick together, gradually growing larger until they become pebbles, then boulders, and eventually the cores of rocky planets. Every atom in your body passed through clouds of cosmic dust at some point, riding these particles through the galaxy before being incorporated into our sun and Earth. The iron in your blood, the calcium in your bones, and the oxygen you breathe all drifted through space as dust before becoming part of you. We are quite literally children of the darkness. The elements in your body were once scattered through clouds of interstellar dust. Every element heavier than hydrogen and helium was forged inside stars and scattered into space when those stars died, drifting as tiny grains of cosmic dust before being gathered into new stellar systems. The carbon in your cells was created by nuclear fusion in the cores of ancient red giant stars, while the oxygen you breathe was produced in massive stars before they exploded as supernovae. These elements did not travel alone through the cosmos, but attached themselves to dust grains, coating particles of silicate and carbon with ices and organic molecules. For millions of years, your atoms drifted through the cold darkness of interstellar space as specks of dust, waiting to be swept up by the gravitational collapse that would form our solar system. You are made of material that once floated silently through the void. The darkness shaped you before the light. And from the dust that made us, we turn to the mysterious zones near the galactic center, where violence and beauty coexist in shadow. The galactic bulge is a dense region of old stars surrounding the central black hole. At the heart of the Milky Way lies a densely packed spherical region of stars known as the galactic bulge, containing billions of ancient suns crowded into a relatively small volume of space. Unlike the flat disk where our sun resides, the bulge is a three-dimensional concentration of stars, many of them older than the disk, and formed in the earliest epochs of galactic history. The stars here orbit in complex patterns, moving both around the galactic center and vertically through the bulge itself, creating a swirling reservoir of ancient light. This region is difficult to study because it lies behind vast lanes of obscuring dust, hiding most of its stars from optical view. Only through infrared and radio observations can we pierce the veil to study these ancient stellar populations. The oldest parts of our galaxy remain shrouded in shadow. Stars in the bulge are among the oldest in the Milky Way, some over 10 billion years old. Many of the stars packed into the galactic bulge formed over 10 billion years ago, making them nearly as old as the universe itself and witnesses to the earliest chapters of our galaxy's long history. These ancient suns were born from gas that had been enriched by only a few generations of previous stars, giving them different chemical compositions than younger stars like our sun. By studying the light from these bulge stars, astronomers can read the chemical history of the early Milky Way, learning about the first supernovae and the rapid star formation that occurred when our galaxy was young. These stars have completed billions of orbits around the galactic center, survivors of an era we can barely imagine. Their light carries information about conditions that existed before the Earth formed. They are the elders of our galaxy. The galactic center is a chaotic environment with intense radiation and gravitational forces. The region surrounding Sagittarius A-star is one of the most extreme environments in the Milky Way, where intense radiation, powerful magnetic fields, and overwhelming gravitational forces create conditions unlike anywhere else in our galaxy. Stars crowd together so densely that collisions and close encounters happen frequently, flinging stars onto wild orbits or stripping material from their outer layers. High-energy particles stream through this region, accelerated by magnetic fields and shock waves, bathing everything in radiation that would be fatal to life as we know it. Clouds of superheated gas swirl around the central black hole, occasionally falling inward and releasing bursts of energy across the electromagnetic spectrum. Despite the violence, this chaos remains hidden behind dust that screens it from ordinary view. The heart of our galaxy beats unseen. Young massive stars orbit dangerously close to the central black hole. Within just a few light years of Sagittarius A-star, astronomers have discovered a cluster of young massive stars that should not exist so close to a supermassive black hole. The gravitational tides near the black hole are so very immensely strong that normal gas clouds cannot collapse to form stars. Yet here we find dozens of hot blue stars that are only a few million years old. How these stars formed remains a great mystery. Perhaps they migrated inward from farther out or formed from a disk of material that once orbited the black hole itself. These stars live fast and die young, burning through their nuclear fuel at tremendous rates and destined to explode as supernovae within a few million years. Their presence so close to the black hole challenges our understanding of star formation. Even in the most hostile environment, stars somehow find a way. One star called S2 completes an orbit around Sagittarius A-star in just 16 years. Among the stars orbiting close to the supermassive black hole, one named S2 has been studied intensively for decades, completing a full orbit every 16 years at distances that bring it remarkably close to Sagittarius A-star. At its closest approach, S2 passes within just 17 light hours of the black hole, closer than any other known star, experiencing gravitational forces that would tear apart less compact objects. By tracking the motion of S2 with extreme precision, astronomers have measured the mass of the central black hole and tested predictions of general relativity in ways impossible elsewhere. Each orbit provides new data, confirming that space and time behave exactly as Einstein predicted even in this extreme environment. S2 is a natural laboratory for testing physics at the edge of what we understand. The star dances with darkness. At its closest approach, S2 travels at nearly 3% the speed of light. When S2 swings around the supermassive black hole at its closest point, it accelerates to a velocity of nearly 8,000 kilometers per second, roughly 3% of the speed of light, and fast enough to cross the entire Earth in less than 2 seconds. At these velocities, relativistic effects become measurable, with the star's light shifting toward longer wavelengths as gravity and motion combine to stretch the light waves. Astronomers have detected this gravitational redshift precisely, providing direct confirmation of general relativity in the strong field regime near a supermassive black hole. The star's time also runs slightly slower than time here on Earth due to both its velocity and the gravitational well it inhabits. S2 experiences the universe differently than we do, stretched and slowed by forces beyond our everyday experience. Speed and gravity warp reality. The region near the black hole experiences time differently due to gravitational warping. Near Sagittarius A-star, where gravity is immensely strong, time flows more slowly compared to regions farther from the black hole, an effect predicted by Einstein's general theory of relativity and now confirmed through observations. A clock placed close to the black hole would tick more slowly than an identical clock here on Earth, with the difference becoming more pronounced the closer you approach the event horizon. For objects orbiting very near the black hole, this time dilation is measurable, and for anything approaching the event horizon itself, time would appear to nearly stop from an outside observer's perspective. This warping of time is not an illusion, but a real physical effect, part of the fabric of spacetime curving under the influence of mass. Near the center of our galaxy, time itself is distorted. The darkness bends not just light, but time. Radio waves and X-rays allow us to peer through the dust toward the galactic center. Although visible light cannot penetrate the thick dust between us and the galactic center, other forms of radiation pass through relatively unhindered, allowing astronomers to study this hidden region. Radio waves with wavelengths much longer than dust particles sail through the interstellar medium as if it were transparent, revealing the radio emission from Sagittarius A-star and the structures around it. X-rays produced by superheated gas and energetic processes near the black hole also escape the dusty veil, detected by space telescopes orbiting above Earth's atmosphere. Infrared light, while partially absorbed, can penetrate enough to reveal individual stars orbiting near the black hole. Together, these different wavelengths paint a picture of the galactic center that would otherwise remain invisible. We have learned to see with eyes beyond our own, perceiving the hidden heart of the galaxy. And as these mysteries settle around you, let the weight of the day drift away like dust dispersing in the void. Take a slow breath and feel your body becoming lighter, carried gently by these facts to fall asleep to in this sleepy science journey. The Fermi Bubbles are enormous structures of gamma rays extending above and below the galactic plane. Rising from the center of the Milky Way like vast invisible wings, the Fermi Bubbles are gigantic structures of high-energy radiation that stretch above and below the galactic disk in perfect symmetry. These bubbles emit gamma rays, the most energetic form of light, produced by particles accelerated to near light speed as they stream outward from the galactic center. The bubbles appear as two enormous lobes, each extending roughly 25,000 light-years from the galactic plane, together spanning a distance greater than the separation between our Sun and the galactic center. Within these structures, cosmic rays and magnetic fields interact to produce the gamma radiation that space telescopes detect. The bubbles are invisible to our eyes and were only discovered through specialized instruments capable of seeing this high-energy radiation. Our galaxy harbors invisible giants. These bubbles stretch 50,000 light-years from the galactic center. The combined extent of the Fermi Bubbles reaches approximately 50,000 light-years from end to end, a distance so vast that light itself would take 50 millennia to travel from one edge to the other. Each bubble is roughly spherical, though their precise shapes are difficult to determine given that we observe them from inside our galaxy rather than from an external viewpoint. If we could see these structures with our eyes, they would dominate the night sky, spanning from horizon to nearly overhead and covering more than half of the visible heavens. The scale of these bubbles suggests that whatever created them released an enormous amount of energy in a relatively short period of cosmic time. They dwarf every visible structure we can see with our eyes in the night sky. Our galaxy has produced something truly immense and completely hidden. They may have been caused by a past eruption from the central black hole millions of years ago. The leading theory for the origin of the Fermi Bubbles suggests they were created by a massive outburst from Sagittarius A-star millions of years ago, when the supermassive black hole consumed a large amount of material and released tremendous energy in powerful jets. During this active phase, the black hole may have briefly behaved like the cores of distant active galaxies, blasting particles outward at tremendous speeds and inflating these enormous bubbles of energetic gas. Another possibility is that an intense burst of star formation near the galactic center triggered powerful stellar winds and supernovae that combined to create these structures. Either way, the bubbles represent a record of past violence at the heart of our galaxy, frozen in gamma rays for millions of years. What created them remains uncertain. Our galaxy has a violent hidden history. The energy required to create the Fermi Bubbles is almost beyond comprehension. To inflate structures the size of the Fermi Bubbles required an energy output equivalent to millions of supernovae, a release of power that defies our everyday understanding of physical processes. Estimates suggest the energy contained within the bubbles equals roughly the total energy the Sun will emit over its entire 10 billion-year lifetime, compressed into a cosmic eruption lasting perhaps just a few million years. This energy continues to power the acceleration of particles within the bubbles, generating the gamma rays we detect today. The sheer scale of power involved suggests that only the most extreme events in galactic physics could create such structures, whether feeding of the central black hole or coordinated stellar explosions near the core. Numbers this large become meaningless to human intuition. We can measure what we cannot truly comprehend. We only discovered these structures in 2010 because gamma rays are invisible to our eyes. For thousands of years, humans gazed at the Milky Way without knowing that enormous gamma ray bubbles extended above and below the band of light they observed. Gamma rays cannot penetrate Earth's atmosphere and are invisible to human vision, so these structures remained completely unknown until the Fermi Gamma Ray Space Telescope detected them in 2010. Even then, recognizing the bubbles required careful analysis of gamma ray data to separate this signal from the background radiation pervading the galaxy. The discovery revealed that our understanding of the Milky Way was dramatically incomplete, that gigantic structures had existed around us completely unseen for billions of years. Technologies we developed only recently have revealed a hidden dimension of our galaxy. The universe contains more than our eyes alone can show us. And from these vast invisible bubbles, we drift into the quiet outer reaches where the galaxy fades into the emptiness between stars. The outer disk of the Milky Way becomes increasingly sparse and dark. As you travel outward from the galactic center, the density of stars gradually decreases until the once brilliant disk of the Milky Way thins into scattered points of light, separated by vast dark gulfs of nearly empty space. The outer reaches of the galactic disk contain far fewer stars per unit volume, and these stars are often older and dimmer than the bright young stars found in the inner regions. Interstellar gas and dust also become rarer, meaning new star formation has largely ceased in these distant zones. The outer disk is a lonely place where the night sky would appear far emptier than what we see from Earth, with fewer stars to illuminate the darkness. A planet orbiting a star in these outer regions would experience a profound isolation from the rest of the galactic community. The galaxy ends not with a boundary, but with increasing emptiness. Stars in the outer regions are separated by vast distances with little interstellar matter between them. In the outer galaxy, the typical distances between neighboring stars stretch to many light years, with little gas or dust filling the intervening void. Unlike the inner regions where molecular clouds and dust lanes provide material for new star formation, the outer disk is relatively swept clean, leaving only the stars that formed long ago drifting through nearly empty space. The stellar density drops so dramatically that a civilization living in the outer galaxy would see far fewer stars in their night sky, perhaps only a handful of visible points of light rather than the thousands visible from Earth. Interstellar travel would become even more daunting, with vast empty stretches between the rare stellar systems. The isolation of the outer galaxy is profound. Where stars are few, darkness fills the spaces between. The edge of the galactic disk is not a sharp boundary, but a gradual fading into emptiness. There is no clear line where the Milky Way ends and intergalactic space begins, only a gradual thinning of stars, until the density becomes so low that we can no longer meaningfully speak of a galaxy at all. The disk continues outward, becoming ever more tenuous, with scattered stars appearing at greater and greater distances from the galactic center. Some estimates place the edge of the stellar disk at roughly 50,000 light-years from the center, but individual stars exist beyond this nominal boundary, wandering through the vast interstellar darkness. The transition from galaxy to void is gentle rather than abrupt, a fading away rather than an ending. Beyond the last scattered stars lies the halo, then the dark matter that extends even farther, and finally the true emptiness between galaxies. The galaxy dissolves into darkness. Some ancient stars have been flung to the outermost edges, orbiting in lonely isolation. Scattered through the outer reaches of the Milky Way are ancient stars that have been gravitationally flung to enormous distances from the galactic center, now orbiting in near-complete isolation. These stars may have been ejected by close encounters with other stars, by disrupted binary systems, or by gravitational interactions during the mergers of smaller galaxies with our own. Some of these outcasts are among the oldest stars in the galaxy, formed in the early universe when the Milky Way was still assembling itself from smaller fragments. They orbit slowly through the outer halo, taking hundreds of millions of years to complete a single circuit around the galaxy, passing through regions where no other stars may be visible to the naked eye. These lonely wanderers have seen the galaxy from its outermost edges for billions of years. They orbit in silence through the cosmic dark. High-velocity stars are ejected from the galactic center and travel outward at tremendous speeds. Occasionally, a star receives such a powerful gravitational kick that it begins racing outward from the galactic center at velocities far exceeding normal stellar motions, becoming what astronomers call a hypervelocity star. These rare objects travel at speeds of several hundred to over 1,000 kilometers per second, fast enough that some will eventually escape the gravitational pull of the Milky Way entirely. The most likely mechanism for creating hypervelocity stars involves binary star systems passing too close to Sagittarius A-star, where tidal forces tear the pair apart and fling one star outward at extreme speed. These ejected stars carry information about conditions near the supermassive black hole, allowing us to study the galactic center through its refugees. They are cosmic cannonballs, fired from the heart of the galaxy. Speed carries them toward eternal exile. Some hypervelocity stars will eventually escape the Milky Way entirely. Among the fastest stars in our galaxy, a select few are traveling so quickly that they will eventually break free from the Milky Way's gravitational embrace and sail off into the vast emptiness of intergalactic space. These escape velocity stars carry enough kinetic energy to overcome the combined gravitational pull of all the matter in our galaxy, both visible and dark, and will one day leave our cosmic home behind forever. The journey to intergalactic space will take millions of years, during which the escaping star will pass through the outer halo and beyond the realm of any satellite galaxies. Eventually, it will find itself alone in the void between galaxies, surrounded by nothing but darkness and the faint glow of distant galactic islands. These stars will become true cosmic wanderers, eternally exiled from any galactic community. They will drift through the darkness forever. And from the fleeing stars at the edge, we turn to the ghostly remnants of galaxies that the Milky Way has consumed. The Milky Way has cannibalized smaller galaxies throughout its history. Our galaxy did not grow to its current size in isolation, but by consuming dozens of smaller galaxies over billions of years, stripping them of their stars and absorbing their matter into the ever-growing body of the Milky Way. When a small galaxy falls toward our own, gravitational tides stretch it into long streamers of stars that wrap around the Milky Way before eventually dispersing into the general stellar population. Evidence of these cosmic meals is written in the orbits of stars and the chemical compositions of stellar populations that differ from native Milky Way stars. The process of consumption continues even today, with several dwarf galaxies being torn apart by our galaxy's immense gravitational pull. Our galaxy is a predator growing larger by consuming its smaller neighbors. The Milky Way was built from the corpses of smaller galaxies. Stellar streams are the stretched remains of dwarf galaxies torn apart by our galaxy's gravity. When a small galaxy or star cluster falls into the gravitational influence of the Milky Way, tidal forces begin to stretch it along its orbital path, creating long, thin ribbons of stars called stellar streams. These streams can extend across vast portions of the sky, wrapping around the Milky Way like ghostly ribbons marking the paths of consumed galaxies. By tracing the positions and motions of stream stars, astronomers can reconstruct the orbits of the disrupted systems and learn about the gravitational field of our galaxy, including the distribution of invisible dark matter. Dozens of stellar streams have now been identified, each one a fossil record of a past galactic encounter. The sky is crisscrossed with these ghostly remnants, invisible to the naked eye but revealed through careful surveys. Our galaxy wears the ribbons of its prey. The Sagittarius dwarf elliptical galaxy is being absorbed by the Milky Way right now. On the far side of the Milky Way lies a small galaxy called the Sagittarius dwarf, which is currently being pulled apart by our galaxy's gravity in a process of cosmic cannibalism that has been ongoing for billions of years. This small dwarf galaxy has already completed several orbits around the Milky Way, losing stars with each passage until only its dense core remains intact. The stars stripped from the Sagittarius dwarf now form a vast stream that wraps around our galaxy multiple times, creating one of the most prominent and best-studied stellar streams visible in the sky. Within another billion years, the remaining core will likely be completely destroyed, its stars absorbed into the Milky Way's halo population. We are witnessing galactic digestion in progress, a slow death playing out over cosmic time. A small galaxy dies as we watch. Its stars loop around our galaxy in a vast stream spanning 300 degrees of the sky. The stellar stream torn from the Sagittarius dwarf galaxy wraps almost completely around the Milky Way, spanning more than 300 degrees of the sky and containing millions of stars that once belonged to this now disrupted neighboring galaxy. If we could see this stream with our eyes, it would appear as a faint band crossing much of the night sky, a ghostly ring marking the orbit of a dying galaxy. The stream has been mapped by tracking stars with similar chemical compositions and velocities, revealing its full extent for the first time only in recent decades. Stars at different parts of the stream were stripped at different times, with the oldest debris now spread so widely it has nearly merged with the Milky Way's own stellar population. The stream tells the story of many orbital passages and many billions of years. The ghost of a galaxy encircles our own. The Gaia Sausage was an ancient galaxy swallowed by the Milky Way billions of years ago. Roughly 10 billion years ago, the young Milky Way collided with another galaxy of substantial size, an event now known as the Gaia Sausage Collision, because the debris stars follow elongated sausage-shaped orbits through the galactic halo. This was not a minor merger, but a significant event that reshaped our galaxy, puffing up the disk and contributing a large fraction of the stars now found in the inner halo. The collision deposited enough stars and dark matter to fundamentally alter the Milky Way's structure and may have triggered the formation of the thick disk that lies beneath the thin disk where our sun resides. We discovered this ancient merger only recently, through data from the Gaia spacecraft that revealed the distinctive orbital signatures of the debris stars. A ghost galaxy hides within our own. We carry the remains of this collision in our galaxy's bones. Remnants of this collision still orbit through the galactic halo as ghostly stellar populations. The stars deposited by the Gaia Sausage merger billions of years ago still orbit through the Milky Way's halo today, following paths that retain the memory of their violent origins. These debris stars have distinctive chemical signatures that differ from stars born within the Milky Way, allowing astronomers to identify them among the native population. They tend to follow highly elongated orbits that plunge through the inner galaxy before swinging back out to great distances, creating the sausage-like distribution in velocity space that gave the merger its name. By studying these ghostly stellar populations, we can learn about the properties of the galaxy that was consumed and the dynamics of the merger itself. These stars are fossils from a collision that happened before our sun existed. The halo holds the memory of ancient violence. And from the consumed galaxies of the past, we move to the invisible satellite galaxies that orbit unseen around us. The Milky Way has dozens of small satellite galaxies, most too faint to see. Orbiting around the Milky Way are dozens of small satellite galaxies, most of them far too faint and diffuse to be visible to the naked eye or even to early telescopic surveys. These dwarf galaxies range from relatively bright systems like the Magellanic Clouds to extremely faint objects containing only a few thousand stars scattered across regions of space where a normal galaxy would hold millions. Many satellites were only discovered in the past 2 decades through deep surveys that could detect their sparse stellar populations against the background of more distant galaxies. The number of known satellites continues to grow as surveys probe ever fainter populations, suggesting that many more remain undiscovered, lurking in the darkness around our galaxy. A whole family of small galaxies accompanies us. Most of our neighbors remain invisible. Some of these dwarf galaxies contain more dark matter than visible stars. The faintest dwarf galaxies orbiting the Milky Way are dominated by dark matter to an extraordinary degree, with ratios of dark to visible matter reaching hundreds or even thousands to 1. In these systems, the visible stars are merely tracers floating within vast halos of invisible material that provides most of the gravitational binding force holding the entire galaxy together. By measuring the velocities of the handful of stars within these dwarfs, astronomers can calculate the total mass and discover that far more matter exists than the stars alone could provide. These dark matter-dominated systems are valuable laboratories for studying the nature of this mysterious substance, offering clues that larger galaxies cannot easily provide. In some of these dwarfs, light is almost an afterthought. The darkness is not empty, but filled with unseen mass. Ultra-faint dwarf galaxies were only discovered in the last 2 decades. Before the digital sky surveys of the 21st century, astronomers had no idea that an entire population of incredibly faint dwarf galaxies orbited the Milky Way, hidden by their extreme faintness and low surface brightness. These ultra-faint dwarfs contain only a few hundred to a few thousand stars, spread so thinly across space that they are almost invisible against the foreground of Milky Way stars. The discovery of these systems has more than doubled the number of known satellite galaxies and challenged theories of galaxy formation that did not predict such tiny systems could exist. Each new survey reveals additional ultra-faint dwarfs, suggesting that the true population may be far larger than we currently know. We have only recently learned that our galaxy is surrounded by ghosts, the faintest galaxies hid in plain sight for centuries. These tiny galaxies may hold clues to the earliest stages of cosmic evolution. The ultra-faint dwarf galaxies orbiting the Milky Way formed in the early universe, when conditions were very different from today, and their stars preserve chemical fingerprints from those ancient times. By studying the oldest stars in these dwarfs, astronomers can learn about the first generations of stars that formed after the Big Bang, including their masses and the elements they produced before exploding. These tiny systems have been relatively isolated for billions of years, evolving slowly and retaining their primitive compositions without the complex chemical enrichment that larger galaxies experience. In a sense, ultra-faint dwarfs are cosmic fossils, preserved relics from an era when the universe was young and galaxies were just beginning to form. They offer windows into a past we cannot directly observe. The smallest galaxies remember the oldest secrets. The dark satellites orbiting the Milky Way may outnumber the visible ones many times over. Cosmological simulations predict that the Milky Way should be surrounded by hundreds or even thousands of small dark matter halos, each one potentially hosting a tiny satellite galaxy or perhaps containing no stars at all. The number of known satellite galaxies has grown dramatically in recent decades, but the count still falls short of theoretical predictions, leading to what astronomers call the missing satellites problem. One possible solution is that many satellites exist, but contain so few stars they have not yet been detected, lurking in the darkness beyond our surveys. Another possibility is that some dark matter halos never formed stars at all, existing as invisible gravitational companions without any visible component. These dark satellites would be completely undetectable by light. Our galaxy may be orbited by ghosts we cannot see. Gravitational interactions with these satellites shape the structure of our galaxy. The satellite galaxies orbiting the Milky Way do not simply float passively through space, but interact gravitationally with our galaxy, influencing its structure in subtle but measurable ways. When a satellite passes through the outer disk, it can create ripples in the stellar distribution, warping the disk and leaving oscillations that persist for millions of years. The influence of the Sagittarius dwarf galaxy may have triggered spiral waves in the disk and contributed to the warped shape of the outer Milky Way that astronomers have observed. Even the dark matter halos of satellites exert tidal forces that affect the motions of stars in our galaxy's halo, creating patterns that reveal the presence of otherwise invisible companions. Our galaxy is not isolated, but constantly feels the gravitational touch of its neighbors. The satellites leave their marks on us. The Magellanic Clouds are our largest satellite galaxies visible from the southern hemisphere. Visible from Earth's southern hemisphere as two fuzzy patches of light, the large and small Magellanic Clouds are the most prominent satellite galaxies of the Milky Way, containing billions of stars and rich populations of gas and cosmic dust. These galaxies lie roughly 160,000 light-years away and are actively forming new stars, unlike the quieter dwarf galaxies that orbit elsewhere around our galaxy. The Magellanic Clouds have been known to southern peoples for thousands of years and were noted by European explorers during their voyages, eventually receiving their name from navigator Ferdinand Magellan. They orbit the Milky Way as a pair, gravitationally bound to each other as well as to our galaxy, and may be on their first close approach rather than long-term residents. These brilliant neighbors illuminate the southern night. They are visitors from the cosmic outskirts. Even these bright companions are trailed by streams of gas pulled away by the Milky Way's gravity. As the Magellanic Clouds orbit through the outer regions of the Milky Way, our galaxy's immense gravitational field steadily pulls gas away from these smaller systems, stripping material that trails behind in long streams extending across vast distances. The gas torn from the clouds stretches across vast swaths of the sky, invisible to the eye but detectable in radio wavelengths where hydrogen atoms emit faint radiation. This stripping process has been ongoing for hundreds of millions of years, slowly depleting the gas reservoirs of the Magellanic Clouds and feeding material into the Milky Way's halo. Eventually, the clouds will lose most of their gas and cease forming new stars, their stellar populations aging without renewal. The Milky Way is slowly consuming its largest satellites. Even the brightest companions are being drained. And as these galactic companions drift through your thoughts, let your mind become as still as the space between stars. There is nothing to solve, nothing to hold. Let each breath carry you deeper into peaceful rest, surrounded by the gentle science of the cosmos. The Magellanic Stream is a ribbon of gas stretching halfway across the sky. The gas pulled from the Magellanic Clouds has formed an enormous structure called the Magellanic Stream, a vast ribbon of hydrogen that stretches more than 100 degrees across the southern sky, spanning a total distance of over 500,000 light-years. This stream contains enough gas to form hundreds of millions of stars, material that will eventually fall onto the Milky Way and potentially fuel future star formation in our galaxy. The stream follows the orbital path of the Magellanic Clouds, trailing behind them like a cosmic wake, and may have a leading arm of gas ahead of the clouds as well. If we could see hydrogen gas with our eyes, the Magellanic Stream would be one of the largest structures visible in the night sky. It is invisible to us, but radio telescopes reveal its full majesty. An enormous river of gas flows unseen above us. This stream is invisible to the eye, but glows faintly in radio wavelengths. The Magellanic Stream remains completely invisible to human vision because the gas it contains emits no visible light, but hydrogen atoms in the stream produce faint radio emissions at a wavelength of 21 centimeters that radio telescopes can detect. This radiation arises when the electron in a hydrogen atom flips its spin relative to the proton, releasing a tiny amount of energy that builds up into a detectable signal when trillions of atoms are involved. By mapping these radio emissions, astronomers have traced the full extent of the Magellanic Stream and measured its structure in remarkable detail. The stream contains not just neutral hydrogen, but also ionized gas that emits in ultraviolet wavelengths, revealing an even more complex structure than radio observations alone can show. This invisible river connects the clouds to our galaxy. Hidden streams flow through the cosmic dark. Cosmic rays are high-energy particles that travel through the galaxy at nearly the speed of light. Streaming invisibly through the Milky Way are cosmic rays, particles accelerated to tremendous energies by violent events like supernova explosions and processes near black holes. Despite their name, cosmic rays are not rays of light, but rather particles, mostly protons and atomic nuclei, traveling at velocities so close to the speed of light that relativistic effects become important. These particles carry enormous amounts of kinetic energy, with the most powerful ones packing as much punch as a fast-thrown baseball despite being smaller than an atom. Cosmic rays pervade the galaxy, bouncing off magnetic fields and wandering through interstellar space for millions of years before escaping or colliding with something. They are an invisible population of high-speed travelers. The galaxy is filled with speeding bullets we cannot see. These invisible particles constantly pass through your body without you ever noticing. At this very moment, as you rest quietly and listen, cosmic ray particles are passing through your body at nearly the speed of light, traversing your tissues without interacting with most of the atoms they encounter. Several cosmic rays pass through you every second, having traveled across the galaxy for millions of years, only to complete their journey by zipping through you unnoticed. Occasionally, a cosmic ray strikes an atom in your body and causes a tiny amount of damage, contributing to the natural background radiation that all life on Earth has evolved to tolerate. High-altitude airplane flights expose passengers to significantly more cosmic rays than ground level, as the atmosphere provides shielding that diminishes with altitude. These messengers from violent cosmic events pass through us constantly. We are transparent to the galaxy's speeding particles. The origins of the most energetic cosmic rays remain a mystery. While most cosmic rays can be traced to supernova remnants and other known sources within the Milky Way, the most energetic particles carry so much energy that no known process in our galaxy can explain their acceleration. These ultra-high-energy cosmic rays must come from extraordinary events, perhaps from the jets of distant active galaxies or from unknown processes that physics has yet to explain. When these rare particles strike the atmosphere, they create cascades of secondary particles that can be detected by ground-based observatories, allowing scientists to study energies far beyond what any particle accelerator on Earth can achieve. Despite decades of investigation, the exact sources of these extreme particles remain uncertain. They arrive from directions that do not clearly point to known astrophysical objects. The most powerful messengers carry secrets we have not decoded. And from the particles passing unseen through everything, we turn to the hidden structures revealed only by new technologies. The galactic magnetic field threads through the entire Milky Way, invisible yet powerful. Throughout the Milky Way, an invisible magnetic field permeates the interstellar medium, threading through gas clouds, dust lanes, and the empty spaces between stars. This magnetic field is far weaker than the field surrounding a refrigerator magnet, yet across the vast scales of the galaxy, it exerts significant influence over the behavior of charged particles and the structure of gas clouds. The field follows the spiral arms of the galaxy, wrapping around them in complex patterns that astronomers have only recently begun to map in detail. Magnetic fields in the galaxy store enormous amounts of energy and can shape the dynamics of entire regions, influencing star formation and the propagation of cosmic rays. This invisible web connects distant parts of the galaxy in ways we cannot directly see. The Milky Way is threaded with invisible magnetic currents. This magnetic field shapes the motion of charged particles and cosmic dust. The galactic magnetic field does not merely exist passively, but actively influences the motion of charged particles and dust grains throughout the entire Milky Way. Cosmic rays, which are electrically charged, spiral around magnetic field lines and bounce off irregularities in the field, causing them to wander through the galaxy in random walks that can take millions of years. Dust grains become aligned with the magnetic field, with their long axes preferentially oriented perpendicular to the field direction, causing starlight passing through dusty regions to become polarized in distinctive patterns. This polarization allows astronomers to trace the magnetic field direction even in regions where the field cannot be measured directly. The tiny and the swift alike respond to these invisible forces. Magnetism guides the unseen through the cosmos. Radio telescopes have mapped the magnetic field's swirling patterns across the galaxy. Using radio observations of polarized emission from the galaxy, astronomers have created detailed maps of the magnetic field structure, revealing swirling patterns that follow the spiral arms and extend into the halo above and below the disk. These maps show that the magnetic field is not uniform, but varies in strength and direction across the galaxy, with reversals and turbulent regions mixed with more ordered structures. The technique of Faraday rotation, which measures how the polarization of radio waves rotates as they pass through magnetized plasma, has proven especially valuable for tracing the field in 3 dimensions. Each new survey reveals more complexity, with smaller-scale structures nested within larger patterns. The magnetic field of our galaxy is intricate beyond imagination. Radio waves have painted the invisible magnetic canvas. The spiral arms of the Milky Way contain stronger magnetic fields than the spaces between them. The magnetic field strength varies across the Milky Way, with the spiral arms containing stronger fields than the regions between them, a pattern that reflects the compression of gas and field lines as material flows into the arms. Within the arms, the field is amplified by the same processes that concentrate gas for star formation, creating environments where magnetism plays a particularly important role in regulating how stars form. The enhancement of the magnetic field in spiral arms helps explain certain features of the polarization patterns observed across the sky and provides clues about how the arms maintain their structure over long periods. This connection between visible spiral structure and invisible magnetic patterns reveals how deeply intertwined different aspects of galactic physics truly are. The arms glow with enhanced magnetism. The spirals are magnetic as well as stellar. Synchrotron radiation from electrons spiraling in magnetic fields reveals hidden galactic structure. When high-energy electrons spiral around magnetic field lines, they emit a type of radiation called synchrotron radiation that can be detected by radio telescopes, revealing structures that would otherwise remain invisible. This radiation depends on both the density of energetic electrons and the strength of the magnetic field, making it a powerful tool for mapping the hidden magnetic architecture of the galaxy. Synchrotron emission has revealed filaments, loops, and shells in the galactic halo that trace outflows from active regions and illuminate structures far from the disk. The polarization of synchrotron radiation also carries information about the magnetic field orientation, allowing astronomers to construct detailed models of the galactic magnetic structure. Electrons dancing in magnetic fields betray the invisible to our instruments. They light up what our eyes cannot see. The galactic wind is a flow of charged particles streaming outward from the disk. Rising from the disk of the Milky Way is a constant outward flow of hot gas and charged particles known as the galactic wind, driven by the energy released by supernova explosions and the radiation pressure from massive stars in active regions. This wind carries material out of the disk and into the halo, enriching it with heavy elements forged in stars and potentially expelling some gas entirely from the gravitational embrace of the galaxy. The galactic wind helps regulate the amount of gas available for star formation, acting as a pressure release valve for the energy injected by stellar processes. Similar winds blow from other galaxies, particularly those with high rates of star formation or active galactic nuclei at their centers. Our galaxy breathes, exhaling hot gas into its surrounding halo. An invisible wind flows constantly above and below us. And from the invisible winds, we drift to consider what we have yet to discover about our galactic home. We have mapped less than 1% of the stars in the Milky Way in detail. Despite decades of dedicated observation and the revolutionary data from spacecraft like Gaia, we have detailed measurements for less than 1% of the stars in our galaxy, leaving the vast majority known only through statistical estimates and sampling. The Gaia mission has measured positions and motions for nearly 2 billion stars, an astonishing achievement, yet this represents only a tiny fraction of the estimated 200 to 400 billion stars that populate the Milky Way. Many stars are too faint, too distant, or too obscured by dust to be individually catalogued, especially those on the far side of the galaxy or in the crowded central regions. Each new generation of telescopes reveals more stars, but the complete census remains far beyond our current capabilities. We have only sketched our galactic home. The full portrait lies beyond our present reach. The far side of the galaxy remains largely unknown, hidden behind the bright bulge and dust. The opposite side of the Milky Way, the regions beyond the galactic center from our perspective, remains one of the least explored territories in our entire galaxy because the bright bulge and dense dust lanes block our view entirely in visible light. Stars and structures on the far side cannot be seen optically no matter how powerful our telescopes may become, leaving us dependent on radio waves, infrared light, and other wavelengths that can penetrate the intervening material. Even with these tools, observations of the far side are challenging because signals must travel through the crowded central regions and contend with confused backgrounds. We know more about the structure of many distant galaxies than we do about half of our own galactic home. The far side is hidden territory indeed. We cannot see our own galaxy's backyard. Radio astronomy has revealed spiral arms on the opposite side of the galaxy. While optical telescopes cannot see through the galactic center, radio observations of hydrogen gas and masers have mapped spiral arms on the far side of the Milky Way, extending our knowledge of galactic structure into previously invisible regions. By tracking the velocities of gas clouds and using the Doppler shift of radio emissions, astronomers can determine distances to structures across the galaxy and place them in a three-dimensional map. These observations have revealed that spiral arms continue on the far side, wrapping around the galaxy in patterns that broadly match theoretical models, though many details remain uncertain. The radio sky shows a different Milky Way than the optical sky, revealing structures hidden from ordinary view. We have glimpsed the far side through radio eyes. The invisible cosmos has yielded some of its secrets. The exact number of spiral arms in the Milky Way is still debated by astronomers. Despite living inside the Milky Way, we still do not know with certainty how many spiral arms our galaxy possesses, with estimates ranging from 2 major arms to 4 or more, depending on which tracers are used and how arm segments are connected across the disk. Different populations of stars and gas trace the spiral pattern differently, with young massive stars and gas showing clear arm structures, while older stars reveal a smoother distribution. The difficulty of measuring distances accurately across the galaxy complicates efforts to connect arm segments into a coherent global picture, leaving room for competing interpretations of the data. Even the names of the arms vary between different research groups and epochs of study. Our home galaxy keeps some of its most basic architecture mysterious. We do not fully know the shape of our own house. Our position inside the galaxy makes it difficult to see its true shape. Living inside the Milky Way presents unique challenges for understanding its structure, much like trying to understand the layout of a forest while standing among the trees with no elevated vantage point available. We cannot step outside our galaxy to photograph it from above, and the confusing overlap of near and far stars makes it difficult to discern which stars belong to which structures. The galactic center lies hidden behind dust clouds that block visible light, and distances to individual stars are notoriously difficult to measure accurately, introducing uncertainties into every structural model. Astronomers must piece together the galaxy's shape using statistical methods, velocity measurements, and comparisons with similar galaxies viewed from outside. We are mapmakers who have never seen the territory from above. Our galactic self-portrait is drawn from fragments and inference. We only confirmed the Milky Way has a central bar in the 1990s. For most of the 20th century, astronomers debated whether the Milky Way was a simple spiral galaxy or a barred spiral with an elongated central structure, and it was only in the 1990s that infrared surveys provided conclusive evidence for a central bar. The bar stretches roughly 27,000 light-years across, oriented at an angle to our line of sight, and contains billions of older reddish stars packed together more densely than in the surrounding disk. This discovery changed our understanding of how our galaxy functions, since barred structures influence the flow of gas, trigger star formation, and affect orbital dynamics throughout the inner regions. We lived for centuries without knowing one of the most distinctive features of our own galactic home. The central bar was hidden in plain sight. We discovered our galaxy's core shape only recently. And from the discoveries still to come, we turn to the dark future that awaits our galaxy. The Milky Way and Andromeda galaxy are destined to collide in about 4 billion years. Measurements of Andromeda's motion show that it is approaching the Milky Way at roughly 110 kilometers per second, and gravitational calculations confirm that the two galaxies will collide in approximately 4 billion years from now. This may sound catastrophic, but galactic collisions are not violent events for individual stars because the distances between stars are so vast that direct collisions are extremely unlikely. Instead, the galaxies will pass through each other, their shapes distorting under mutual gravitational influence, before falling back together over hundreds of millions of years in a complex gravitational dance. The collision will trigger new rounds of star formation as gas clouds compress and fragment under tidal forces. Our galaxy has a destiny written in the motions of distant light. Two spirals will become one. When they merge, the night sky will transform with new stars blazing into existence. As the Milky Way and Andromeda interact during their long gravitational encounter, vast clouds of gas will be compressed by gravitational tides and shockwaves, triggering intense bursts of star formation that will light up the combined galaxy with hot blue stars and brilliant glowing nebulae across thousands of light years. The night sky from any surviving planet would be transformed, with brilliant new star clusters appearing where before there was only darkness and streamers of stars arcing across the heavens as tidal forces reshape both galaxies. This starburst phase will last tens of millions of years, creating a temporary blaze of stellar activity before the gas is exhausted and the merged galaxy settles into a quieter state. The collision that destroys will also create. The merger will be a cosmic firework display that lasts for eons. The two supermassive black holes will eventually spiral together and merge. At the center of both the Milky Way and Andromeda lies a supermassive black hole, and when the galaxies merge, these two cosmic giants will begin a slow gravitational dance that ends in their eventual coalescence into a single, even more massive black hole at the center of the combined galaxy system. Initially, they will orbit each other at distances of thousands of light years, but dynamical friction from surrounding stars and gas will cause them to spiral inward over hundreds of millions of years. As they approach each other more closely, they will begin to emit gravitational waves, radiating energy and spiraling ever faster until they finally merge in a cataclysmic event that briefly outshines all the stars in the combined galaxy. The resulting black hole will be the new dark heart of the merged galaxy. Two hearts of darkness will become one. This collision will send gravitational waves rippling through space-time. As the two supermassive black holes spiral together and merge, they will generate gravitational waves so powerful that they will ripple across the entire observable universe and far beyond, distorting spacetime itself as they propagate outward at the speed of light. These waves will be too low in frequency for current detectors like LIGO to observe, but future space-based observatories may be able to detect similar mergers in distant galaxies. The merger will release more energy in gravitational waves than our Sun will produce in its entire 10 billion-year lifetime, yet this energy will be almost entirely invisible to ordinary telescopes, passing through matter without interacting in any detectable way. A universe of gravitational waves already surrounds us from ancient mergers. Our future collision will add its own ripples to this cosmic symphony. In the distant future, the merged galaxy will become an elliptical shape, losing its spiral arms. After the Milky Way and Andromeda have fully merged and the turbulence has settled over billions of years, the resulting galaxy will have lost its beautiful spiral structure and become an elliptical galaxy, a smooth, featureless ball of stars without clear arms or disk or any of the elegant structure we see today in either of the progenitor galaxies. The violent gravitational interactions during the merger will have scattered stars onto random orbits, destroying the ordered rotational motion that creates spiral patterns. The merged galaxy, sometimes called Milkomeda or Milkdromeda by astronomers today, will be dominated by older reddish stars, with little gas remaining for new star formation. Our spiral home will someday exist only in ancient light traveling through the cosmos. The elegant spiral will become a placid ellipse. As the universe expands, other galaxies will drift beyond our view, leaving us alone. The expansion of the universe is accelerating, driven by the mysterious force called dark energy, and in the far future, this expansion will carry distant galaxies beyond the cosmic horizon, the point beyond which light can never reach us no matter how long we wait. Galaxies that are currently visible will fade from view one by one as the expansion carries them away faster than light can travel across the growing void. Eventually, the only galaxies remaining visible will be those gravitationally bound to our own local group, primarily the merged remnant of the Milky Way and Andromeda. Future astronomers, if any exist, will see an empty universe beyond their own galaxy, with no evidence of the billions of galaxies that exist today. The universe will seem to shrink even as it expands. Our cosmic neighborhood will become an island in apparent emptiness. Eventually, the night sky will contain only the stars of our merged galaxy. In the distant future, the night sky will contain no galaxies beyond our own, no Andromeda smudge to inspire wonder, no distant spirals to study through telescopes, nothing but the stars of our own merged galaxy and the deep darkness between them stretching to infinity. The cosmic microwave background, that ancient echo of the Big Bang, will have redshifted beyond detection, erasing the most important evidence of the universe's origins. Future beings would have no way to deduce that the universe was once smaller, hotter, and filled with countless galaxies stretching to the horizon in every direction. The observable universe will have contracted to a single galaxy floating in apparent emptiness, with no clues to its true history or the vastness that once was. The evidence of cosmic history will be erased by time. Future skies will hold only local stars. The rest of the universe will vanish beyond the cosmic horizon forever. As dark energy continues to drive the acceleration of cosmic expansion, galaxies beyond our local group will cross the cosmic horizon one by one, their light redshifting toward infinite wavelength and fading to nothing as they recede into the unreachable distance far beyond any possible observation. Once they cross this boundary, no signal from them will ever reach us again, no matter how long we wait or how sensitive our instruments become. The universe will not have been destroyed, it will simply have become forever inaccessible, a realm of existence that continues but can never be observed or contacted by any means. This is the loneliest possible future, a single galaxy adrift in apparent void with no evidence that anything else exists or ever existed. The cosmos will seem to end at the edge of one galaxy. The universe will vanish without disappearing. And as the distant future fades into silence, let your own thoughts grow still. The darkness ahead is not empty, it is patient and peaceful. Let your breath slow and allow yourself to drift into the gentle embrace of rest in this sleep documentary of cosmic wonders. Star formation in the Milky Way will eventually exhaust all available gas. The Milky Way forms new stars at a rate of roughly 1 to 2 solar masses per year, drawing upon reservoirs of cold molecular gas that will not last forever even on cosmic timescales. While some gas falls into the galaxy from the surrounding intergalactic medium, and gas can be recycled through stellar winds and supernovae, the overall supply is gradually being depleted as new stars lock up material in their nuclear cores. In tens of billions of years, the rate of star formation will decline as the raw material runs low, and eventually the galaxy will be utterly unable to create new stars at all. The last generation of stars will be born into a galaxy that has already seen trillions of years of stellar activity, inheriting the heavy elements of countless ancestors. Star formation will eventually become a memory. The cosmic nursery will close forever. In trillions of years, the last stars will burn out and the galaxy will grow dark. The longest-lived stars in the cosmos are small, cool red dwarfs that burn their hydrogen fuel so slowly and so efficiently that they can shine for many trillions of years. Far longer than the current age of the universe allows us to observe their full lifetimes. But even these patient, enduring flames will eventually exhaust their fuel and fade into cold, invisible remnants drifting through an empty galaxy. In the far future, the last red dwarf will finally die, and no new stars will form to replace it, leaving the galaxy populated only by the cold remnants of stellar evolution. The night sky will contain no shining stars, only the invisible remains of suns that once burned brightly. The galaxy will enter an era of darkness that may last far longer than the era of light. The stars will go out one by one. Eternal night will settle over the cosmos. White dwarfs will cool over countless eons, becoming black dwarfs that emit no light. After stars like our sun exhaust their fuel, they shed their outer layers and leave behind dense cores called white dwarfs, which slowly radiate away their residual heat into the coldness of space over unimaginably long timescales, stretching far beyond anything we can directly observe today. Given enough time, these white dwarfs will cool until they no longer emit any detectable light, becoming theoretical objects called black dwarfs that would be nearly impossible to detect across interstellar distances. The cooling time for a white dwarf to become a black dwarf is estimated to exceed 10 quadrillion years, far longer than the current age of the universe. No black dwarfs exist today because the cosmos is simply not old enough. The final stellar embers will take eons to grow cold. The last light will linger for unthinkable spans of time. The universe is not old enough yet for any black dwarf to exist. The universe is approximately 13.8 billion years old, a span of time that seems unimaginably vast by human standards, but is actually quite brief on the timescales required for white dwarfs to cool into black dwarfs. Even the oldest white dwarfs, formed from the very first generation of stars in cosmic history, are still radiating detectable light and will continue to do so for many trillions of years to come. The black dwarf is therefore a theoretical object, predicted by physics, but never observed because the conditions for its existence have not yet had time to develop anywhere in the cosmos. We live in an early cosmos, still young and bright, where even the oldest stellar remnants still glow with residual heat. The age of black dwarfs lies immeasurably far in our future. The universe must grow much older before darkness claims its final form. Eventually, black holes will dominate the dark galaxy, evaporating slowly through Hawking radiation. In the far future, after all stars have died and white dwarfs have cooled to black dwarfs, black holes will become the dominant remaining structures in the dark galaxy, slowly evaporating through a process called Hawking radiation over timescales that dwarf all previous cosmic history. This radiation is emitted because quantum effects near the event horizon allow particles to escape, carrying away mass and energy over inconceivably long timescales. The supermassive black hole at the galactic center will take roughly 10 to the 100th power years to evaporate, a number so vast it defies human comprehension. Eventually, even the largest black holes will vanish, leaving nothing but a thin bath of particles and radiation. The final act of cosmic history will be excruciatingly slow. Black holes will be the last monuments to a universe that once burned bright. And from the far reaches of cosmic time, we return to the present and the dark wonders still surrounding us tonight. Even now, countless hidden objects drift through the Milky Way unseen. At this very moment, the Milky Way is populated by countless objects that remain invisible to our telescopes, from rogue planets wandering without stars to brown dwarfs too cool to shine brightly. from black holes lurking in the dark to stellar remnants that emit no detectable radiation at wavelengths we can easily observe. These hidden objects outnumber the visible stars in ways we are only beginning to understand, filling the spaces between the bright points with a population of dark wanderers moving through the galactic void. Some of these objects pass through our solar neighborhood regularly without ever being detected by any instrument we have built. The dark side of the Milky Way is not a region but a population, the countless invisible inhabitants sharing our galaxy. The unseen far exceeds what we can observe. We are surrounded by hidden neighbors we may never know. The nearest star to the Sun was hidden from us until 1915. Proxima Centauri, the closest star to our Sun at just over 4 light-years away, was not discovered until 1915 when the Scottish astronomer Robert Innes identified it while carefully searching for any stellar companions to the bright Alpha Centauri system. Despite its remarkable proximity to our solar system, this small red dwarf had escaped detection for all of human history because its faintness made it invisible to the naked eye and difficult to pick out from the crowded stellar background. The discovery reminded astronomers that even our nearest cosmic neighbors can remain hidden in plain sight, and it hinted at how many faint objects might populate the spaces between stars. Our closest stellar neighbor was unknown until remarkably recently. The nearest star hid for millennia. Proximity does not guarantee visibility in the cosmos. Proxima Centauri is too faint to see with the naked eye despite being our closest stellar neighbor. Despite being the nearest star to our solar system, Proxima Centauri is far too dim to be seen without a telescope, shining at roughly 1/7% of the Sun's luminosity and appearing as an 11th magnitude object that requires optical aid to detect even under perfect dark sky conditions. This faintness is due to its nature as a red dwarf, a small, cool star that converts hydrogen to helium at a miserly rate compared to larger stars. If you stepped outside tonight and looked toward the southern constellation Centaurus, you would see Alpha Centauri A and B as a bright point, but Proxima would remain invisible, hiding just 2 degrees away in the dark. Our nearest stellar neighbor requires a telescope to be seen at all. The closest star is hidden by its own faintness. Even nearby, the dark side prevails. The darkness between stars is not empty, but filled with particles, gas, and energy. The vast spaces between the stars of the Milky Way, which appear utterly empty to our eyes, are actually filled with a thin interstellar medium of gas atoms, dust particles, cosmic rays, and magnetic fields that permeate the entire galactic disk and extend into the halo. On average, there is roughly 1 atom per cubic centimeter in interstellar space, far emptier than any vacuum we can create on Earth, but not truly empty in the absolute sense. This tenuous medium plays crucial roles in galactic ecology, serving as the raw material for new stars and transmitting energy and matter across vast distances between stellar systems. Cosmic rays from distant supernovae thread through this space, carrying information about violent events from across the galaxy. The darkness between stars is a medium, not a void. What appears empty is merely sparse. The Milky Way is a living archive of cosmic history, written in light and shadow. Every star, every dust cloud, every invisible stream of dark matter in the Milky Way carries information about the history of the cosmos, stretching back billions of years to the earliest epochs of structure formation. The chemical composition of ancient stars records the nucleosynthesis of previous stellar generations. The orbits of stellar streams trace the gravitational scars of galaxies consumed long ago. The distribution of dark matter reflects the initial conditions of the early universe. The Milky Way is not merely a collection of stars, but a vast archive of cosmic events stretching back to the formation of the first structures in the universe. By studying our galaxy, we read the story of the cosmos itself, written in patterns of light and shadow. The Milky Way remembers what has passed. Our galaxy is a book written in light and shadow. And so our journey through the hidden face of the Milky Way draws softly to a close. In this sleep documentary, we have wandered through the unseen corners of our galaxy, from the supermassive black hole lurking at its heart to the dark matter halo wrapping around us like an invisible embrace. We have drifted past stellar nurseries hidden in dust, past the ghostly remnants of swallowed galaxies, past rogue planets wandering in eternal night. These sleepy science facts have carried us through realms that light cannot reach, where the deepest truths of the cosmos rest in patient silence. If this journey has brought you peace, know that you are welcome here whenever sleep feels far away. New wonders await in future nights, more gentle science for sleep to guide you into rest. Consider subscribing to continue exploring the universe one peaceful fact at a time. Right now, as you lie here, the dark side of the Milky Way continues its endless work around you. Dark matter threads through the walls of your room, cosmic rays pass silently through your body, and somewhere in the galaxy, stars are being born in clouds you will never see. You are part of this vast, hidden cosmos, breathing softly within its ancient arms. If your eyes feel heavy, let them close. There is nothing left to see tonight but the gentle darkness behind your eyelids. Let your breath become slow and deep, like the turning of a galaxy that takes 200 million years to complete a single rotation. Feel the tension in your shoulders dissolve. Let your jaw soften. Let your hands rest open. You have carried enough today. Now the universe will carry you. Tonight, as you rest, the dark side of the Milky Way continues its patient existence. Black holes spin in silence, dark matter holds the stars in place, and cosmic dust drifts slowly through the void. Somewhere, a new star is being born in a cloud no telescope has ever seen. Somewhere, a rogue planet drifts alone through the endless night, and you are a small, warm presence within this vast galactic darkness, peacefully resting among the hidden wonders. Sleep well, sweet dreams. And may you carry with you the quiet knowledge that even in the darkest corners of the cosmos, something extraordinary is always happening, patient and eternal, waiting to be discovered. This has been Drowsy Discovery. Good night.